And here we go. Hey, what is up guys? Welcome once again to the channel. It's always great to have you back. And I'm pretty sure that you have been working with ChatGPT either for work stuff or if you're a student with some problems or exercises. And I was wondering, how good is ChatGPT in chemical engineering, but more properly, chemical reaction engineering problems? So is it true that it's going to already substitute the chemical reactor designers, or maybe not? Let's check it out. So let's get started with this exercise. So actually, I have been working with the chemical reaction engineering bundle, which is going to have a lot of chemical reaction engineering courses, mostly based on Fogler's book, but of course I'm going to be adding more information from other books and more importantly, a more updated approach towards the problems. And yes, I have a traditional exercise 2.9, applications of batch stoichiometry tables. This is from the rate law and stoichiometry. And yes, essentially what I'm going to be doing is copying all this content. As you can see, there's a lot of questions. So I'm going to see whether or not ChatGPT is going to be able to first understand the questions, second, work through the problems, third, explain correctly those approaches, and finally, whether or not the final result is correct. So I'm going to be, and here we go. So I'm stating clearly that this is a chemical reaction engineering problem. It may be useful to state that as a context. Giving the oxidation of naphthalene to phthalic anhydride will be studied. So taking A as a basis of calculation, and I'm not going to be adding extra information. A right here is, of course, talking about the initial limiting reagent. So let's see if the AI can cover that. We have this reaction right here. I'm pretty sure that ChatGPT will going to verify whether or not the reaction is correct or so. Let's see how it goes. For the case in which 3.5% of naphthalene, A, and 96.7% of air, which is 20% of oxygen, is going to be react. So right away, as you can see, this is directly from the problem. And yes, it is incorrect. The correct percentage should be 96.5%, of which 21 could be assumed to be oxygen. We have pressure and temperature conditions. Fit under these conditions, naphthalene is the limiting reagent, and we want to solve for a batch reactor system. Fill up the stoichiometry tables. We are not letting the AI know that this is actually a isothermal design, but we are going to be calculating initial concentrations. And then we need to set up functions of conversion of species B, non-isothermal, non-isobaric conditions, then isothermal and isobaric conditions. We also need to calculate the volume of the system at any time. Remember that technically speaking, this is not at any time, is at any extent of reaction. Calculate the pressure of the vessel and find the reaction rate at any conversion value. Okay, so let's see how it approaches this. Okay, so I really like that the ChatGPT is already adding steps it's going to be explaining, because I didn't actually tell the AI or the ChatGPT to explain individually the steps, so that's great. Now making stoichiometry tables, yes, these are correct. Now A, B, C, D, E initially, the changes, and the final amounts. So one thing I'm seeing right away is that this is already assuming complete interaction, or there's no actually account for the initial amount of feed. Step number 2, calculate the initial concentration of A. And I really see right away that the AI is assuming a feed, which you shouldn't be doing because you already have pressure, temperature, and some amount of this material right here, which you can assume that these are both gases because naphthalene needs to be burning on gas phase. I don't like this part right here because concentration could be calculated with the ideal gas law. We are also okay, so this is still information. The initial moles, okay, this is calculating under the basis of 100 moles, which once again, I really don't like. You shouldn't be adding this assumption of 100 moles, or maybe yes, you could do it, but not in order to assume later on that this is the actual final amount of moles. So the initial amounts calculated right here. Okay, yeah, I'm okay with that. This is total amount of oxygens. Step number 3, set up a function of I don't know what, they're not stating, versus conversion of species B. Now this is once again incorrect. If we're talking about XA, we're talking about conversion of A, so it doesn't make that much of a sense to be working with species B. But nonetheless, let's assume this is correct. And yes, we have the molar balance, total flow rate. This is continuing to make. Okay, so it's trying to identify the initial value. Now we're using the ideal gas law, but we are not finding any type of concentration that's later on going to be used in the rate of reaction, which actually we don't need right now, but eventually will be nice to have. To fully solve, okay, we need additional data such as rate law, or rate constants, and specific reaction mechanism. So although this may be kind of true, in reality you don't need to have this because we are just making a theoretical approach. We're just going to set up values for X in the theoretical assumption that X can go to the 100%, the conversion of the limiting reagent. Although this could be technically correct, you could still do it theoretically. Fill up stoichiometry tables. I'm not really happy with the way this stoichiometry table is set up. There is no extent of reaction. It's not based in any kind of species. This is a generic stoichiometry table. As you can see, yes, we know that the change are the actual stoichiometry, but you need to account for initial amounts, the inert amounts if there's any, if you're making concentration calculations and so on. So I will state a score of 4 out of 10 because although it may read the problem, it's not understanding the problem, it's not properly explained, it's not actually solving, and it's not actually getting the right answer. So what I'm going to be asking ChatGPT now is to set up the general mole balance equation for several types of reactors, and not only generic. I want them in molar flow rates, I want them in concentration, and I want them in conversion. So let's go and check it out. Make, in the context of chemical reaction engineering, make a general molar balance equation for the CSTR tank or reactor in concentration terms, conversion terms, and flow rate terms. Okay, so let's see how it goes. Okay, this is so far correct. We have the reaction, we have the stoichiometry coefficients of A, B, C, and D. I don't know why they added E. Typically will not be used, but it's okay. So first things first, I'm not liking that they are making the general mole balance. I would really love to have that the accumulation term equals the inlets, outlets, generation, or the consumption and production, but okay. Let's assume so far this is correct. Okay, concentration terms. We have it here in conversion terms. Okay, so something I'm not liking that much is that it has the integrals or differential parts. I would really love for ChatGPT to propose the final version, as you can see here. What I'm looking for in conversion of the CSTR is a worked solution. We have flow rate of A initially, conversion of A, and the rate of reaction right here. For the flow rate, okay, generally speaking, this is not so bad, but once again, it's not fully developed. So we have conversion, flow rates, and we don't have concentration terms. Okay, so yeah, you could say that this is the concentration terms one. Since there is no change with respect to time, this will be correct. Actually, you see here, you will have FA0 minus FA equals, okay, we have something like this divided by volume, and we have this times volume. So no, I'm not quite happy with this solution. It's going to be canceling 0. So yeah, we could say overall speaking, it is kind of correct. Of all terms, concentration terms will be the one that approaches the most to this solution. Concentration terms. Now the one on conversion, no, I didn't like it that much. And the one of flow rates, no, I didn't like it that much because if you were to integrate this, there is no change with respect on time to the CSTR. So technically speaking, the rate of reaction of A times volume is going to be 0, which doesn't make that much of a sense. If we were to score out of 10, I will score this maybe 3 out of 10 because one, yeah, they kind of understand the question. So, okay, explain is incorrect. The whole explanation doesn't make that much of sense. It's like a Frankenstein, they are adding a lot of things that doesn't make that much of a sense. So if you were to read them alone, they make sense, but in the context, doesn't make that much of a sense. The explanation is not so great. The work through of mathematics, it's, I would say, the best of the 4 things. And finally, the solutions are incorrect. They are not proposing the correct solutions. So actually I will ask, why are you including differentials if CSTR is steady state? Okay, so what's going to be doing, ChatGPT is going to be correcting and reworking. This is great because, as you can see, now we have 0, not the differential. This makes much more of a sense. Now, if you were to solve for this will be actually correct. In concentration terms, no. Actually, this is mostly in flow rates, but okay, we can assume that concentration, flow rates can be worked. Conversion terms, okay, so where is conversion? Right here? We even have it proposed, but we don't have it in the equation. And in flow rate terms, well, yeah, this will be okay. Let's assume that this is a better solution, but what I didn't like is that I had to know that this is steady state and let the chat remember that this is steady state. Okay, now let's work another problem maybe. Okay, this one looks interesting. So we have, first, in the context of chemical reaction engineering, the elementary liquid phase reaction, and we are given the reaction, is carried out isothermally in a CSTR. Now, pure A, which is right here, is already fully defined, enters at a volumetric flow rate of 25 cubic decimeters per second at a concentration of 0.2 mole per cubic decimeters. Now, the main question will be, what CSTR volume is necessary to achieve a 90% conversion? Given that the rate constant K is equal to 10 cubic decimeters per mole second. Okay, let's see how it goes. So to determine the CSTR volume necessary to achieve 90% conversion, we can use the molar balance equation. Thanks, that makes sense. Given the data, we have K, volumetric flow rate, okay, concentration of A initially, or at inlet, that's great, beautiful. Desired conversion at 90% or 0.9 fractional. So far, very good. The molar balance equation for species A in the CSTR is given as follows. 0 equals volumetric flow rate of A initially minus the volumetric flow rate of A in the outlet minus the rate of reaction times volume. So I'm not liking that we're talking about volumetric flow rate of A. Typically, we like to use flow rates of A or molar flow rates, but because the volume is constant, yeah, technically speaking, we could use it. Not the typical approach, but I will say it's good enough. Let's continue. The rate of reaction is given here, rate law. So yes, this is correct. The rate law is correct. I don't like that they're not using the negative sign, but that's okay. It may be convention stuff. Since stoichiometry of the reaction is 2A2 converts to B. Okay, so yeah, the concentrate. Okay, this is okay so far. I'm not going to be complaining. I would prefer using molar flow rates, but if we use concentration, since this is liquid, we can assume constant volume. I don't like that they're not letting you know that this is only valid in liquid phase, but okay, no need to. We are giving the following Q concentrations and K. So now let's proceed to the calculations. Let's see, for the conversion, we're going to find out the final concentration, which is this one right here. Yes. Okay, so this is the outlet concentration. I'm very happy with that. Calculate the rate of reaction. Yes, this is a correct step. We will need to input this data right here. And I don't know what's the C dot PS per second, concentration per second, I don't know. Okay, so the rate is correct. The units are strange, but yeah, let's assume it's correct. Then we're going to be substituting 25, the volumetric flow rate, The outlet volumetric flow rate, we don't know it. We know the rate, and the volume of the tank is something we don't know. Okay, so this is something I'm not liking, and this is why we shouldn't be using liquid flow rates. We are assuming that the outlet flow rate is changing with respect to A. So yes, technically speaking, yes, but this is not making sense because we're talking about moles. Either we use concentration or molar flow rates, and we end up with this part right here. Let me go back here, and yes, as stated before, if we have the following flow rate design equation, we calculate it for the molar flow rate going in, the initial concentration, conversion, the rate of reaction law. So here what we said, essentially we calculate the rate of reaction, which is correct, 0.004. Okay, so far was okay, but the calculation is kind of incorrect. We didn't have the flow rate, we didn't have the conversion. Although the conversion is affecting the volumetric flow rate, it's not affecting the actual molar flow rate. Hence, that's why we have another number right here. If the correct answer is, how will you fix this? So let's see if we provide a correct answer, if it could be rearranged, or maybe the chat is going to try to understand it. No, it's not liking. If you have further questions. So I don't like that the chat is not trying to play this game of theoretical thinking and trying to go reverse engineering. So let's actually try to reverse engineer the solution. If volume was equal to, let's give another opportunity. So actually it's not reversing, it's doing exactly the same. Let's go back again. I really love how they actually understood the question. So I'm going to be adding maybe 7 out of 10. It actually understood the problem. It also worked through the solutions. The steps were kind of correct in most cases. The last step was incorrect, but overall was a good approach. I didn't like that the explanation was kind of separated per steps, but okay, I'm going to be, let's say, I'm going to assume that it was correct. And finally, the final answer was totally incorrect, but at least it made sense, and it was something that, okay, it's kind of related towards the volumetric flow rate or so. So that's why I'm going to be adding a 7 out of 10. So far, the best solution of the questions that we have been asking. What I want to do in this exercise is a plain question. So in isothermal reactor design, why is plug flow reactor typically smaller in volume than the CSTR? I really love this part. For certain type of chemical reactions due to their respective flow patterns and a nature of reactions. Okay, let's see more about that. Okay, we're talking about residence time, the reaction rate, okay, back mixing. No, so actually I just wanted to see a very simplified version of whenever performing the general molar balance equation. Actually, let's do so. Can you focus this question explaining with the general molar balance of the reactors? Okay, what's going to be doing is developing the general molar balances of the both and comparison. Okay, let's see the conclusion, because it's like explaining the same stuff all over and over. Conclusion: for the same reaction and under the same conditions, the plug flow reactor and CSTR will achieve the same level of conversion. Okay, yeah, exactly. That's what we're talking about. We want the same conversion. What we're talking about is volume. However, due to different reaction profiles and constant reaction rate in PFR, it can achieve the desired conversion with a smaller volume compared to the CSTR, which operates at constant volume and at constant reaction rate. Kind of satisfied with the question. I will be adding 8 out of 10. It really understood the question. It worked it through it. I just had to add an extra prompt. And the conclusion makes sense. The final solution is also correct. So yeah, I will be adding 8 out of 10. So that's it, guys. Those were 4 main questions, some theoretical questions, some numerical problems. And I really think that for theoretical questions, they may be okay for definitions, for topics, maybe for rephrasing questions or problems could be okay. But if you were to make these problems, I wouldn't strongly recommend it. It seems that whenever we are talking about theoretical concepts and mathematical concepts, it kind of mixes a lot of the mathematics, and a lot of the theoretical questions doesn't make that much of a sense when we're talking about accumulation or the differentials. When we're talking about conversion, it also seemed that it couldn't differ, conversion of A, conversion of B, limiting reagent. So it doesn't follow the typical chemical reaction engineering methodology. So I wouldn't encourage this specifically for chemical reaction engineering, but for theoretical questions, I will say it's okay. But generally speaking, I would rather go and check out problems from books or university web pages rather than assuming ChatGPT is giving me the correct answers. And the problem is that ChatGPT doesn't know whenever it has a mistake or error, pretty similar to a human, of course. But the main problem is that we are assuming that this is the correct knowledge. So yes, that's up to you guys. What do you think? Do you really think ChatGPT is going to improve in the next, I don't know, 3 to 6 months? Or do you think that still this type of analytical thinking is very hard for a ChatGPT? Remember that it is trained on the content that is given, all the input, but it also generates stuff. So that's the interesting part. From the things that we are giving to the chat, analyzing all the stuff, all the input that we are giving into it, how it thinks and learns, and eventually how it generates the final results or the output. So very important to ensure correct prompts, very important to add the context, try to help the chat in order to understand what you're looking for. If you want a molar balance, if you know that, for instance, you need to be working with moles, maybe state that you need to do so. If you want the certain type of species, you already know the limiting reagent, add the more information. And I really think this is going to be very interesting in the following 1 to 2 years, because we are going to be adding a lot of input from the online data, and it's going to be making very interesting solutions. But as you can see, it is still important for a chemical engineer or an actual engineer to check out the results, because we need someone to blame. Yes, I know that blame doesn't sound interesting, but if something happens, we need to know who was the one that accepted that generated result. Was it an engineer or was it a computer? Well, that's why we're going to still have chemical engineers for the future. Now guys, let me know what you think on the comment sections. I'm looking forward to see what you think, if you have been already working with it, if you are happy with your study sessions, or maybe you're already working and you really think that I haven't explored the full potential. This was a very easy example on what I will do if I were a student. So far, not so happy, but I'm pretty sure that you have been exploring that niche application of chemical engineering for yourself. So, on my behalf, that will be it, guys. I'll see you in the next video.